Hello everybody. In this video, we'll present Strap's wall element. Wall element can be defined only in 3D models. Space frame. Loads can be applied on a wall element at top and bottom levels only. It is not possible to define an intermediate load between top and bottom levels along the height axis of the wall. In order to define a wall element, the user must first define a wall section. After section definition, in order to define the wall itself, the user must select at least two nodes along the height axis of the structure. Let's define a wall section. Select Walls and Section. In the Wall Sections window, we can see a list with all the wall sections defined in the current model. Edit Add Section will allow the user to edit or define a selected section. Assign Section will allow the user to assign a wall section to an existing wall in the geometry. Delete Section will allow the user to delete a section from the list. Create Section From will allow the user to define a section from a DXF file of a CAD software or beams that are already defined in the geometry. Additionally, the user can reduce the wall stiffness by a factor. The factor defined by the user applies to all the wall sections. This option allows the user to meet the need of different codes to reduce the wall stiffness due to cracked wall section for a specific analysis. Now, we'll define the following wall section. We'll use the option Edit Add Section. Select wall section number 1 and click Edit Add Section. Wall definition is carried out by the definition of segments. The white square on the screen represents the location of the segment start definition. The user must enter the coordinates of the segment end, dx and dy. Dx and dy values can be relative to edge of a segment to edge of a segment or center to center. For example, for segment number 1 definition, if the user selects center to center, the value of dx is 330 centimeters. If the user selects edge to edge, the value of dx is 350 centimeters. Now, let's define segment number 1. On the top of the screen, we can see the segment's number and its thickness. We'll insert the segment end coordinate dx equals 350, dy equals 0, while the option edge to edge is active. In order to end the definition of a segment, the user may select Add Current Segment or press the Enter key on the keyboard. We can see that segment number 1 was defined, and now the white square that represents the next segment's start coordinate is now located at the end of segment number 1. The end coordinates of segment number 2 relative to the white square are dx equals 0, dy equals 220 centimeters. The end coordinates of segment number 3, dx equals 170 centimeters, dy equals 0. The end coordinates of segment number 4, dx equals 0, dy equals 200 centimeters. The end coordinates of segment number 5, dx equals minus 500 centimeters, dy equals 0. Additionally, we can see that within segment number 5 there is an opening. While defining the segment, we'll check the box Has Opening. The opening dimensions are set by the parameters w, opening width, in our case 120 centimeters, and h, opening height, in our case 210 centimeters. The parameters dh and dv we'll set the opening location relative to the start coordinates of the segment. In our case, dh equals 210 centimeters and dv equals 10 centimeters. We can see that segment number 5 was defined with the opening. Now, we'll define segments 6 and 7 together as one segment, and later on we'll define segment number 8. In order to close our shaft section, we must define that the end coordinates of segments 6 and 7 is ending at the corner of another segment, in our case, segment number 1. So in these cases, we won't enter the end coordinates dx and dy, but instead we'll select that the segment ends at another segment end. The button Select Segment End will allow us to select a corner of a segment. We'll select the left corner of segment number 1. Now, we'll define segment number 8. The start coordinates of segment number 8 is at the cross point between segments 2 and 3. In order to move the start point of segment number 8, we'll select Move Mark to another corner under Segment Start. Now we'll select the start point of segment number 8, and we can see that we moved the white square to the desired location. Segment 8 ends within the left segment of the wall section, segments 6 and 7. In order to define the end coordinates of segment 8, we'll select segment ends at within a segment. The Select Segment button will allow us to select the segment at which the current defined segment ends. We'll select the option New segment is perpendicular to end segment. We can see that we defined segment number 8. After defining the section, the user must set the material of the cross-section. Additionally, the user must pay attention to the location of the reference corner, which is represented by the green asterisk. The position of the reference corner will correspond to the location of the nodes that will be used to define the wall in the geometry. Additionally, in the wall section window, there are a couple of more options. Edit a segment will allow the user to edit a segment in the section. Once this option is selected, the user must select a segment, and all of the segment's parameters will be displayed on the screen and can be edited. Delete a segment will allow the user to delete a defined segment. Reference corner will allow the user to set the location of the reference corner. Add section will allow the user to import an existing section to the current section definition. This option can also be used as copy. Unify and split segments will allow the user to unify or split segments. Now, let's define the wall in the geometry. We'll define two nodes along the height axis of our structure, the x3 global axis. Node number 1 will have the coordinates of 0, 0, 0, and node number 2 will have the coordinates of 0, 0, 3. The height of the wall we'll define will be 3 meters. We'll go to Walls and Single Wall. On the bottom left corner of the screen, we can see the wall number and the section that will be assigned to the wall that we are defining. To define the wall, we must select a node that corresponds to the section's reference corner location at the bottom level of the wall, node number 1 in our case, and another node that corresponds to the section's reference corner location at the top level of the wall, node number 2 in our case. We can see that we defined the wall, and the location of nodes 1 and 2 corresponds to the location of the reference corner in the walls section. As mentioned earlier, loads can be applied to wall element only at its top and bottom levels. A wall element must be divided at any level that the user wish to apply loads. Let's see the next example. We can see two levels of slabs, one at +3 and one at +6. The support level is 0. If we'll define a wall with the single wall option and select a node at 0 and a node at +6, the slab at +3 won't be connected to the wall and won't transfer the loads at +3. In order to define the wall correctly, we'll select walls and then the line option. Select a node at 0 and a node at +6. Strap will identify all intermediate nodes along the selection line and divide the wall accordingly. We can see that two walls were defined, and now the loads are transferred from the slabs to the wall correctly at levels +6, +3, and 0. Another command in the Walls submenu is Walls Link. This command will allow the user to link slab elements to the wall and to set the connection type. Let's see the following example. When we ask for data for node number 44, we can see that the node is connected to the wall and to one mesh element. When we ask for data for node number 310, we can see that it's not connected to the wall, it's just connected to the mesh elements. Additionally, we can see that the distance between node 44 and node 310 is 25.7 centimeters. In order to connect the mesh elements to the wall, we'll select Link. The nodes will be connected to the wall by one of the following options. The first option, Strap will embed the node into the wall, like node 44. The second option, Strap will create a linear rigid link to the closest nodes that are embedded in the wall element. The parameters dmin determines if to use the first or the second option. If the distance of the unconnected node to the connected node is greater than dmin, the node will be embedded in the wall. If the distance is less than dmin, Strap will create a linear rigid links. In our example, the distance between node 44 and node 310 equal to 25.7 centimeters, smaller than dmin that equals 40 centimeters. The distance of node 309 from node 44 is 51.4 centimeters, greater than dmin. So, when we apply the link wall command, node 309 will be embedded into the wall, and node 310 will be rigidly linked to nodes 44 and 309. We'll select a pinned connection type and click Continue. Now, we can see that node 310 was rigidly linked to nodes 44 and 309. Node 309 was embedded in the wall. Node 308 was rigidly linked to nodes 309 and 307, and so on. Now, we'll set the parameter dmin to 10 centimeters. Since the distance between the nodes along the wall section is greater than 10 centimeters, all the nodes will be embedded into the wall. we can see that all the nodes along the wall section were embedded into the wall. Another command in the wall's submenu is rotate. The rotate command will allow the user to rotate a defined wall around the height axis at the location of the wall's section reference corner. In the following example, the reference corner location is at the location of nodes 1 and 2. We'll select walls and rotate, select the wall, and select to rotate the wall by 90 degrees. We can see that the wall was rotated by 90 degrees around the height axis at the location of the reference corner. Now, we'll review the graphic result display for wall elements. The model on the screen is built out of two walls, 3 meter height each. We defined a load case with three 200-ton joint loads at the top of the structure. The loads are applied in the global plus x1 direction. To graphically display the wall result, we'll select General Result, Draw Results. In the Display Type drop-down menu, we'll select Wall Results. When we graphically display wall results, the user can choose if to display results for each segment or for the entire wall section. Additionally, the user can choose if to display the result diagram at the screen plane or at the results plane. For this example, we'll display the results of each segment and the result diagram in the results plane. The Result Type menu includes all the wall results that are available for display. We can see different types of results for moment and shear. Moment or perpendicular moment, and shear or perpendicular shear. The display of these results are dependent on the user's selection if to display results at each segment or wall total. If display result at each segment is active, then the result moment is for the moment at the segment plane, and shear is the shear force at the segment's plane. Perpendicular moment is for a moment that is perpendicular to the segment, as well as the shear force. Let's display the moment result at each segment. Since we are displaying the results at the result plane, we can clearly see that the displayed results are for moment at the segment's plane, as for the result for shear. Now let's display the results for perpendicular moment. We can see that the results are for moment that is perpendicular to the segment's plane. As for the results for perpendicular shear. Now, we'll ask to display the results for the entire wall section. At the graphic display window, we'll activate results at wall total. Now, the results moment, shear, and perpendicular moment and perpendicular shear are displayed according to the section definitions in the geometry. Let's go back to the geometry module and review. The following drawing illustrates the result directions. The result moment will be for bending around the vertical y-axis. The result shear will be for shear force in the horizontal x-axis direction. Perpendicular moment will be for bending around the horizontal x-axis. And the result for perpendicular shear is for the shear force in the vertical y direction. Now we'll go back to the results module and review our results. The load case for which we're displaying the results consists of 3 joint loads, 200 tons each, at the level of plus 6 meters from the support level. The load direction is the global axis plus x1. We'll display the result moment for the whole wall section. We can see the moment result, 3,600 ton-meter. And the shear result is constant 600 tons. The result for perpendicular moment is very small, since we haven't defined any loads in the global x2 direction. Additional graphic results that are available for wall elements are axial force and torsion moment. Results for coupling beams at wall openings are also available. Coupling beam moment, coupling beam shear, and coupling beam axial force. This is it for this video. Thank you very much for watching.